Okay. So far we have discussed two types of equalization, the feed-forward equalization and decision feedback equalization. So we'll just discuss some more implementation issues with decision feedback equalizers and wrap up the topic. The main advantage of decision feedback equalization is that to achieve the same amount of equalization, to achieve the same amount of ISI cancellation, they don't enhance the noise, okay? Because the feedback part is digital, which has no noise. Again, the system consists of essentially an IR filter with a slicer or a limiter in the feedback path. Okay. So you can have as many taps as you wish. That is the number of ISI taps that you want to cancel. So if these taps are adjusted to exactly the ISI values, if these taps are set to exactly the ISI values, so ISI is completely cancelled. Okay. Now in a digital implementation, you will have, so let's take a fully digital implementation. That is, you have converted the output of the channel using an A to D converter into a digital form. Okay. How would you implement the slicer? If you have a digital input, how do you slice it? Huh? What's that? I can't hear. Flip-flop. No, you have the input itself is a digital word. How do you do that? Huh? Yeah, input is a digital word. Okay, so what is the, how do you implement that? You just look at the MSB, right? That gives you whether it is greater than or less than something. If it's a 2-level slicer, if it is more than 2 levels, then you have to look at more bits. Okay, so for a binary case, it is just the MSB will tell you if it's plus or minus 1, whether it's in the bottom half of the range or top half of the range. How do you implement the delays? Flip-flops, yeah. I mean, you need to have a register. In this case, it's a single bit if it's a binary stuff. If it is multiple bit, then you need to have so many bits in the register. Okay. How do you implement the coefficients? It's digital, everything is digital. All of these things are digital. So Y is digital. So what you add to that should also be a digital word. How do you do that? Huh? Multiplier, but in case of a binary thing, you need basically a selector, right? You need to either select plus or minus. Okay, so it is a multiplier. It is multiplying this quantity y hat of n minus 1 with C1. But y hat of n minus 1 has a limited number of possibilities. It's in the binary case, it has only 2 possibilities. So then using the binary values, you select either C1 or minus C1. Okay. So essentially, this is not a full blown multiplier. You don't need to do that. Especially in the binary case, it's a selector. Okay. Okay. And if you have more levels in the digital data, then again you can use a selector. Unless you have a very large number, then you may need to implement it slightly differently. Okay. You can always do this, right? You can always, this is like a lookup table. You know, for every possibility of y hat, you compute the output product and then you store it in a lookup table and you select one of them. But of course, if the number of values of y hat becomes very large, that may become too painful. Otherwise, if the number of values of y hat is small, let's say as in the binary case, then you don't have any problem. Okay. And then you need to have adders to implement the subtraction as well as summing of all the weighted taps. Okay. So you have different blocks and there is a constraint on the delay of each of these taps, each of these blocks. Each of these blocks will have a delay when you implement it as a combinational or sequential circuit. Okay. And the total delay must be sufficiently small. I mean, depending on what the total delay is, you can clock it at a certain rate. Okay. So you will have the clock going into this, and so within one cycle you should be able to close the loop. Conceptually it is nothing complicated. So when you start implementing that, you will see the difference. But we won't treat it beyond this. But if you have done a course on digital IC design, you know that you have a loop like this, what is essentially an IIR filter. So whatever, whether it's IIR or FIR, doesn't matter. You have some input, some logic being performed, and some storage and feedback. And for this to work at a certain with a certain clock period, the delay of this has to be limited. Okay. So it's the delay of this plus the clock to Q delay of this and the setup time of the storage element, which is the flip flop. Okay. How many of you are taking digital IC design this time? Okay. So I think you do understand what's going on, right? Now let's go to, if you go to very high speeds, it's not going to be a full digital implementations because the number of taps is going to be small also. Okay. It's just that very high speed that makes it a challenging implementation. So let's say this would be an analog implementation. How would we implement it? We have to implement each of these blocks in analog. How would we do that? How would we implement it? Comparator will be? Yeah, typically the slicer, because you want a high gain, you need a regenerative latch or a flip flop. And you will have the sampling clock here. Okay. And this delay is not Z inverse, but ST by 2. Okay. Now this may not be explicitly implemented delay. It just accounts for the delay of all of these. You adjust the delay of all these blocks so that it becomes approximately half the clock cycle. Okay. In fact, usually at the speeds at which you work, where you have to make these analog equalizers, you don't really implement this e to the minus st by 2. Okay. So you just you have all these analog amplifiers and you make the delay of that appropriate. In this case, no, it is analog. I mean, it is sample data analog, perhaps, or it could be continuous time also. So in this case, we are looking at. So I say y of n, it's really y of t. You have to make sure that the cursor is normalized to 1. Okay. No, see, you are varying the taps, right? No, that's what, like, the value of C1 and C2 will be scaled by the cursor value also. That's true. There should be a, okay, I'll come to that. It's absorbed into the delays of flip-flop and the coefficients. So at the input, the cursor is normalized to 1, meaning it's 1, not 1, but some voltage value. Okay. So let's say 300 millivolts or something. So what you need also, in addition to the equalizer, a variable gain amplifier, which will be adapted so that the cursor becomes 1. Now that's not strictly necessary because if you have a large range of coefficients C1, they can get adjusted to the cursor value times the relative value of the tap with respect to the cursor. Okay. That is, if you implement a response where all the cursor value and all the tap values are scaled, you will implement the same equalizer but with a different gain. But typically in reality you also have a variable gain amplifier here which is adaptively adjusted to give you a desired signal value. How do we implement the coefficients? So in this case again these will be digital values, so you can use differential pairs in the switched region to implement it. Okay. In fact, this entire circuit does look like the transmit equalizer, where you have differential pairs with different tail currents which are tied together. Okay. Any questions on this? It's again conceptually not difficult, and also we have studied these blocks. This is a differential pair and you need to tie a number of differential pairs together, and if you have a limited range for C1, C2 and so on, you implement each differential pair scaled up so that it can only implement that much. That's the maximum value. Because if you try to implement everything so that it can implement the very large tap value, the differential pair becomes very large. So the parasitic capacitance at the common node, it becomes very large. Okay. So then you have to either use a lot of current to drive signals across those parasitic capacitors, or you will be limiting the bandwidth of the entire system. Okay. So the equalizer is supposed to provide high frequency boost and compensate the channel. It will also have to compensate for all the bandwidth limitations that you introduced in your circuit. Okay. So if you have a low pass filter in your circuit, it will have to boost it up so that it will have to provide compensate for that also, because any low pass filter, whether it's the channel or your circuit, it will introduce intersymbol interference. Okay. So clearly in high speed circuit, the key is to minimize all parasitic capacitances so that you don't introduce any bandwidth limitation. It's hard enough to equalize the channels. You don't want to make your job even harder than that. Yeah. Yeah. No, no, it will be linear. It may not be this, it won't be e to the minus st, but some other t1. That is, that's okay to some extent. It's okay to have, see, essentially by the time you sample the next value, you should have the right kind of feedback, the right values fed back. So there is some uncertainty that is tolerable. Okay. So the delay through this can be the symbol period t plus minus some value. Okay. So it's not necessary to have it exactly at t. If it varies a little bit, it changes the shape of the eye diagram, but it may not change the values at the sampling instant too much. Okay. So what will happen is horizontally the eye will maybe become closed a little more. Okay. So some variation is tolerable, and typically you find that using simulations. Right. So you design the circuit and the biasing, because the delay of all these elements depends on their own parasitic capacitances. It's like the delay of an inverter, right? It depends on the GM of the inverter and the parasitic capacitances. Both the parasitic capacitance varies with process and temperature. The GM varies with process temperature and the bias condition. So you adjust it so that the variation is within manageable limits. Okay. Why? No. See, each of these has some delay, excess delay in addition to what it's supposed to do. Okay. There is a delay between the clock and y hat. Y hat doesn't appear at the edge of the clock. Similarly, if this signal changes a little later. Alright. So, if you implement e to the minus st by 2 here using a latch, then the total delay inside this will be more than one period, typically at very high speeds. So, what you have to do is to make the delays of these, delay of this plus this and the summation equal to about half the period. Okay. Because you are going to get more delay than what you actually put in, right? If you put in a flip-flop, you are not going to get just that delay, you will get something more. Now, these will be implemented using D flip-flops, because it is one period with respect to the previous one. Yeah, so depending on how many values you have for coefficient. So what it's implemented, in a way it is a selector, right? So to implement the coefficients in the transmit equalizer, what we did was to vary the tail current. So you select the tail current, that's essentially what it is. Okay. But the output is typically, when you want to do summation in the analog domain, the easiest thing to do is to sum currents, because Kirchhoff's current law, you put all the currents through the same node and it does the summation. Okay. It's harder to sum voltages because you have to put voltage sources in series. So you do this, and the weighting is provided by the tail current I tail. So depending on the coefficient value you want, you choose the value of I tail. Okay. Anything else? Yeah. Yeah, when I say analog implementation, I mean that you do summation and those things in currents and voltages, as opposed to adding numbers, right? Whereas in a digital implementation, you have two digital numbers and you add them using a full adder or something to get the output. Okay. Mathematically, yeah, because you take a channel H and you do 1 over H and you set, right? Yeah. Yeah. Completely closed, yeah. Yeah. Yeah, you can, yeah, even if the eye is completely closed, you can equalize as of course, once it's completely closed, I can't say anything more about the percentage eye opening, right? It is 0. So essentially, as the bandwidth keeps reducing, it gets worse and worse. And usually what happens is, there is a range of eye opening or range of bandwidth for which you can do blind equalization, that is blind adaptation. You have the equalizer, and without any help, with the actual random data, it adapts the right coefficients. Now, as the bandwidth further reduces, you may need to train the equalizer with some known data. Okay? Because now it has a hard time adapting. But it is possible to equalize it. So there are two things, equalization and adaptation. Adaptation is the harder one if you have really bad data. Equalization, mathematically, certainly, if you have h of z, you can implement 1 over h of z. Okay?
What we have in the diagram is the bandwidth is the point that we are equalized.
Yeah.
And there is horizontal shifting of the eye opening is there.
Yeah.
There is something not equally, not 1 to 1 is not the thing.
Okay.
And that also in 1 to 1 also when you see the peak,
Yeah.
there is a horizontal shifting, horizontal crossings are coming near the peak of the eye.
Meaning, then eye is not open.
Eye is not open.
That is strange. Okay, one thing I realized also is that the best thing in this particular case, in the low bandwidth case, you need to have 2 precursor taps. But the way I framed the problem, I have constrained you to 1 precursor tap. It will still equalize it. From my simulations, it looks like it will equalize it. I don't know if the tap values you. Is it? I don't know. I got them to be the same. That's what. Huh? How did you get that? How did you do the minimization? No, but what did you do? Like, how did you? That gives you 4.1? No, I don't know. I mean, the same thing gave me 3.7, I think. You got 4.1. Oh, sorry. No, I know. So when I did A transpose A inverse, A transpose times Y, where Y is 0, 0, 1, that gives 4.1. What did you equalize this to? This is the third one 1 or the second one 1? What is the, why? Third one is 1. Third one is 1, yeah. I have to check it again because this exact thing gave me. Which one? No, this minimizes the mean square error between, see, the coefficient times the equalizer, the channel coefficient times the equalizer, convolved with equalizer coefficient must be something, okay. So this, I don't know, I have to check my code also. Yeah. Okay. Yeah. Yeah. Is it? Okay, I'll have to check my code because no, the one thing is I didn't realize it before, but that's not the optimal case. You should have 2 precursors. But what happens is with this, the eye opening will not go to somewhere near 100%, but I think the best eye opening you get is about 50% or something. 60%. Okay.
How can we extend this horizontal jitter in the crossing? Basically, it should be equal to 50%, right? It should be like complete eye at 50 instead of 50%.
So, what is it that you see? I have a hard time imagining it. Do you see something like this with? So, is it something of this sort?
Even like this, whatever. Yeah.
Huh?
Even in this eye also, if you move to the right side, there are crossings are there.
Where? In this region?
Yes.
So, inside this?
Yeah, inside this there are crossings.
No, then that eye is not open. No, I think, is it because of the starting transient, you have to remove some of the, you have to plot the eye after the coefficients are stabilized, and you have to remove the initial transients of the filter, because the filter, if you don't do anything, it starts with a 0 value, right? I mean 0, there are 8 states in the filter, they'll all start with 0. So if you look at the waveform in continuous time, it will start something like this. And if you include this part of the waveform in the eye diagram, it will look like some trace which is doing this. Okay.
Like not this kind of thing. When you draw a crossing and crossing comes in between this side.
So basically you are saying the eye opening is smaller, right?
Yeah.
What is the eye opening? I mean, how much is the? Okay, is it? Yeah, that's okay. Yeah, that's fine. I mean, it could be that depends on the type of the filter and type of the channel you do, right? There is no reason why the eye diagram has to be symmetric. It is symmetric in many cases, but not necessarily in all the cases, right? If you have first order RC filter, the eye diagram looks like this. Definitely not symmetric in the x direction. So what is the bottom line? The first thing is that the LMS is not converging to the same as manual mean square minimization. And the sin LMS is converging closer to that and also giving a better performance. What I got was the biggest coefficient was 3.7 when I did this, and that is close to what the LMS. Huh? Yeah. No, then the eye opening can't be different, right? The percentage eye opening will be the same in the. Yeah. So, okay, so I'll check that again. But anyway, I think the number of tabs chosen in the equalizer was not also optimal, but besides that, there seems to be some mismatch in what you see. So, anyway, I didn't understand quite your point, what you mean by there are crossings here. You are saying that eye opening is small, right? How much is it? Yeah, there will be, right? I mean, this part is where all the crossings are. That's what I mean by drawing something like this. Yeah, vertically it is symmetric because you have plus and minus 1 symbols. No, it does not, it's not, you don't expect it to be symmetric also. No, that is because the pulse itself looks like that. See, the pulse, it goes from being maybe something like this to perhaps something like this. So the pulse itself has a longer tail on one side, right? Pulse response. So the same thing shows up in the eye diagram also. But I mean, if you do a single RC case, the response will be like this to a single pulse. Sorry, response will be like this. And the eye diagram will look like this, which is also not symmetric in the horizontal direction. What? When you? Yeah. No, but what is the number of coefficients you get with that? Infinity, right? So that's the problem. If you invert it, you get infinite number of coefficients. So you truncate it to some limits. That is the zero forcing case. But that case also introduces a lot of noise. If you add noise, that introduces a lot of gain to the noise. So you do minimum mean square error, which performs better than noise. We haven't proved it, but you can take it that it does in fact better. Huh? Yeah. I can't hear. That's true, but the final value should be the same. Yeah. Yeah, maybe then, I mean, with such a small eye opening, maybe it also has a hard time adapting. No, there is one assumption, right? Because no, there is also one particular assumption that I had mentioned it once. You make the decision, and you say that this error is the difference between the decision you made and the input you get. Okay? But the actual error should be the difference between this and what you sent. That is the actual error. Now this is an estimate of the error. If this is wrong for too many cases, adaptation can be driven in the wrong way. Okay? Slightly different or quite off? What was it? But what did you equalize it to? I mean, what was the difference in the two cases, the initial conditions? Okay. Which one? This is okay. Now, I mean, this could be that, see, depending on the initial condition, maybe this corresponds to, I chose this initial condition because I was imagining one precursor tap and 3 post-cursor taps. Now, if you design an equalizer with 4 post-cursor taps, you will in fact get different coefficients, right? Isn't it? That is probably what you are getting. So, maybe what you are doing is equivalent to having one precursor and, no precursor and 4 post-cursor taps, if you do that. No, but that's what. But if you start with arbitrary coefficients, I am not sure that it will be able to converge that way. Okay. You start with something totally arbitrary. Yeah. Yeah, that's what I am saying. So, what are the coefficients in this case? This is the largest after it settles down? Not necessarily. Huh? It is the largest or no? What about in this case? Is this the largest? The second one is the largest, but it's different from this. Okay, that's again something I have to check. But there is a difficulty in adapting if the error rate is very high, because you are assuming that this error is, this should be the error between what you receive and what you sent. But you are taking the error between what you sliced, assuming that to be more or less correct. If it is correct for enough number of cases, it will drive the equalizer in the right direction. If it is wrong for too many cases, that's why I said maybe this bandwidth was too low. Maybe we should do it with points. Yeah. 0.1 gigahertz. Oh, 1 gigahertz per second. So that's 150. Yeah, I think in that case it can't equalize at all because initially every decision is wrong. Maybe that is the thing. Maybe you should just do it with 0.67 and submit that. Okay. So in these cases, what you need is, that's why you need training, right? In that case, you know what bit pattern you are sending. So you can compute the error with respect to what was actually sent, not what you sliced. I think that is probably what is happening. Maybe I thought that 0.5 was close enough to 0.67 and it will behave similarly, but apparently not. Okay. So, but for 0.67, do you still see the same difference between sign and manual calculation and the full LMS? Have you tried it with 0.67? Okay. So maybe I think you should just do it with this. 0.67 is 0.67, yeah. If you can, I think it should be a matter of small change in the code. So I will check that also, because my manual minimization seems to give a different result. Okay. Huh? No, I am saying the direction in which it drives itself might be. No, I mean, if I say that the largest one is the precursor, largest one is the cursor, then it does, that's what it implies, right? Yeah, that's okay. No, if you restrict the coefficients, there is a distinction. No, if you see, in my definition, cursor is the maximum tap, okay? It doesn't have any special place other than the fact that it is the maximum value, that's all. Okay, so, and also I had given some restrictions on coefficients. I gave the largest range for this and smaller range for these things. So, in that case, it is legitimate to interpret this as the cursor and the rest as either precursor or post-cursor. But if you have unlimited range, yeah, that is another thing. If you let it go unbounded, then also it can fail to converge. That is one reason why you have, you can either have a fixed cursor tap and adapt only the others, or you have a restricted range for those things. Okay. Because, I mean, that you can see, right? If you have a large number of taps, let's say you had a very large number of taps, then the correct coefficients might be, let's say, minus 0.25, 1, minus 0.5, 0.25. So let's say these are the correct coefficients, but my equalizer really has 10 taps. Okay. Now, like what will it converge to? There is an ambiguity. If you have 0, minus 0.25, 1, minus 0.5, 0.25 and all these zeros, it's a good equalizer. If you have two zeros and minus 0.25, 1. So in this case also the eye opening will be the same, right? It's simply delayed. That's all. So unless you restrict the range of coefficients, there is some ambiguity in the convergence as well. Okay. So in practice, you always restrict the values of coefficients so that you can guide the convergence. Because that is why I said maybe when you start from this initial condition, it will converge to something, and if you start from something like this, it will converge to something else. Okay. And if you have unlimited tap ranges for every tap, then there is certainly an ambiguity. You stop meaning, yeah, you restrict the, if it says that, see, like your increment is sine of the error and sine of the gradient. If you are already at the maximum and if this product is positive, you don't increase it anymore. You limit it to that value. Okay. So yeah, if you have unlimited tap ranges, certainly there is an ambiguity, and both are legitimate, both are correct. There is nothing wrong with the two, but you won't necessarily get a unique answer. And of course, this is also an artificial case where everything else will be 0, and in reality that's not true either. Okay. So on this, and we have talked about it a couple of times before, people have raised this thing. So I have a channel like this, and I said you cancel this and think of this as the cursor. The cursor is a sort of arbitrary thing. In my case, I think of the maximum value as the cursor. So let's see what happens if you think of this. And in case of the DFE also, like someone suggested, why not treat the first one as the cursor and cancel the rest? Okay. What will be the disadvantage in that case? Let's say we make a DFE for this. Now this, normally I think of as a precursor ISI. Okay. So I say that I can't use a DFE. But you can equally well say that this is my cursor, right? That's a completely arbitrary distinction. I will say that this is the cursor and I'll cancel this off. What will be the problem? You need to have coefficients larger than 1, but what is the problem with that? That is some implementation detail. We can do that. No, we are talking about DFE. Okay. So, this one I can't make a DFE if I think of this as the cursor. But I can make a DFE if I do think of this as the cursor. Then I make the decision and subtract something, and that ratio that happens to be more than 1, that's all. Okay. That's not a problem at all. Why do you say you need to delay the input? You get some input, that's it. There is no, in case of DFE, you simply have this, for this particular system, you will have no, there is no non-causality, right? There is no non-causality at all. If you have precursor ISI, it just says that the second one is larger than the first one, or some later one, right? So the only thing that means is this, let's normalize everything to, let's say this is 1 and this is half. Okay. Let's say even that's not an issue. Let's say we somehow start it off with the right output. Then it can stay correct, because once the initial value is correct, the next one will be correct and the next one will be correct and so on. So that's true. Because you had the expression for the error, I forget exactly what it was. It was Q of 1 over sigma W divided by 1 plus Q of 1 over sigma W minus something like this, right? So this term grows large, but what is the largest value? It is 1. So there is more error enhancement, okay, but that is still okay. What else is the issue? What will be the bit error rate? Actually, there is something that we have missed in this whole calculation, that is, we assume that the cursor is normalized to 1, okay. So what do you have to do? So let's say this is the response 0.5 and 1. We want to make a DFE for this, okay, and we want to have plus minus 1 samples at this point. Is this a complete system? What else do I need? What will be the value of C1? See, if I want to normalize this to plus minus 1 and this is the response of the channel, what I need is a gain of 2 here, okay, so that this gets normalized to 1 and this C1 value is 2, okay. Now let's not worry about the DFA error propagation and all of that. Let's say it starts off with the right place and does it. So what is the problem with this system? As opposed to, yeah, what's the problem with this issue? It will amplify the noise. So if you treat the small element as the cursor, you will have to amplify it to the right level. Or if you don't amplify it, I mean, again, this plus minus 1 is a kind of arbitrary thing. I can always say plus minus half is my logic 0 and logic 1. But then in that case, whatever it is, for a given noise variance, it is, it's a smaller ratio, right? So you will get a larger error rate. So if you think of this as the cursor and equalize it, you will get you are cancelling the large part and you are left with the small one, you will get a larger bit error rate. Is this part okay? Yeah. Okay. Yeah. I can't hear, I didn't hear the last sentence. Ellipse, yeah, it can be an ellipse. Because the coefficients are not the same, right? Yeah, yeah. Yeah. Yeah, that's true. Yeah, that's, in case of sine, the magnitude of oscillation is just mu, right? So in the other case, perhaps that can happen. So actually, yeah, how did you conclude that the magnitude of oscillation is larger? Huh? That's what you're getting. Okay. Is it for the sine also? Yeah, I mean, see the dynamics of this, yeah, it can happen, because I think if with a PRBS 7 you will get, the coefficients also have a period of 127, right? You will see some pattern like this. I mean, this is about 127 periods, yeah, that can happen, that's true. I don't know if it's necessary, I mean, I don't know how to relate it to this ellipse. I don't know if it is the one with the larger axis or the smaller axis that has more oscillations, but yeah, that's true, it can happen. The chatter in every coefficient will not be the same. If, yeah, that's true. That is also why you, like this truncate, like after a point, there is no point having more taps, because you can't really adapt it very precisely. Firstly, there is this adaptation jitter, and one potential thing you can do is you let it adapt and then stop the adaptation, right? So then the coefficients are exactly constant. But even then, the precision to which it has adapted may not be good enough. So that's why, I mean, I said 0.01, but even much smaller taps you don't realize. So in case of digital adaptation engine, at least there won't be any implementation error. In case of analog stuff, there is even an implementation error. You think you are implementing 0.05 and it can be slightly off. In case of digital, at least that error is not there, so you can implement smaller coefficients. But it generally doesn't pay to implement coefficients like 0.001 and so on. It simply adds more hardware without doing anything to bit error rate. So the point of, I mean, the reason why I keep saying something is the cursor, where it's a relatively arbitrary treatment, is that you would like to I mean, you would like this to contribute to the signal and you cancel the remaining intersymbol interference terms. You can also do the other way. You can retain this and cancel off this. In that case, you will have worse performance because you are treating the smaller one as signal. So for the same amount of added noise, you will have a lower signal to noise ratio or a higher beta rate. Okay. Is this clear? I think you asked about this, right? So actually in reality what happens is there is no clean way of choosing the number of coefficients for a given channel without doing an extensive number of simulations over the channels that you expect and see what the coefficient ranges are and so on. So the number of coefficients as well as the ranges of coefficients are fixed by a lot of I would say engineering, by simulations. So what I did was for the sake of the assignments, I just took some channel, and if it had the largest one and one previous to the largest one and 3 following the largest one, I said the equalizer also has the same thing, but it turns out that's not the optimal either. So if you do the simulation with an equalizer which has the largest one, 2 before it and 2 after it, that gives a better performance. But I don't know how to analytically arrive at this result. Okay. So maybe that should have been part of the assignment also. Any other questions on this, on decision feedback equalization? What do you guys want to do for the final one? I had said that you will have a presentation where you read up some paper and present it. Do you want to do that, or do you want one large assignment? Large assignment. Okay. I mean, you already made it. I mean, something that works. Including transistor level details. Yeah. What is who votes for a presentation? Oh, so you are clearly voting for presentation. What is it? I mean, in this course we can be flexible enough to do it either way. So that's why I'm asking. Presentation? How many vote for presentation? How many vote for? Huh? I mean, not do either and then lose the marks. That is always there. So clearly, I mean, if you have a transistor level adaptive equalizer, that will be more work than preparing for a presentation. In fact, you can not prepare for a presentation and present it also. So I have to compensate for it somehow, but I'll think about it. Okay. Any other questions? Huh? We should have 2 more, but maybe those who are doing the presentation can do a smaller assignment, and those who are doing this can skip the last one or something. Okay. Or at least it can be combined with something else. How many of you are doing a self-study on clock and data recovery? I think for some of you it will be a repeat over there also. Yeah. Yeah. I mean, it's just the evolution of coefficient over time. Why? Why? No, there's only one graph, right? Or maybe mu? 50 graphs. How come? Yeah. So, I mean, this is just to see the long-term trend. I mean, so thankfully it's electronic presentation, but electronic submission. But and definitely don't plot each coefficient of 5-tab equalizer on a different plot, right? That is impossible to comprehend. So what I expect is some tab where one of them goes here and the other one goes here and something. If you plot everything together, that's what it will look like. That gives you an idea of how fast it adapts. And also, I mean, if there are too many points, you can cut it off where it. So one thing I have found in many assignments is you don't use the axis range properly. So if it's, I mean, here we have not dealt too much with frequency response, but the typical frequency response I see is It will be plotted from 1 hertz to 1 gigahertz. The action is somewhere between 100 megahertz and 1 gigahertz. So the plot will look like this, and this will be 0 and this will be minus 300 dB. So basically you can't see anything. That's so you just cut off all the non-essential details and show the necessary ones. Any other questions? Okay, so we meet tomorrow at 9.